Hello everyone, we are Group 5 and today we are excited to present our project titled Intrusion Detection on Network Traffic. This work has been guided under the supervision of Professor Shihyu Shang as part of the Data 245 Machine Learning course at San Jose State University. Our team members are Aishani, Debika, Ketki, myself Rajeshwari and Sheetal. Let's talk about the problem statement, which is malicious traffic detection on encrypted network using time-based features. So in today's world, end-to-end encryption is vital for securing data. However, it also creates a blind spot for traditional security tools by concealing packet content. This allows attackers to hide malware and data exfiltration within encrypted channels. Even with encryption, timing and size-based metadata is still visible. Attackers exploit encrypted channels like TLS SSL to bypass signature-based intrusion systems. Hence, we aim to detect malicious traffic using only time-based features, a strategy that is efficient, privacy-preserving, and hard to evade. Now, why only time-based features? 4 key reasons which we have taken into consideration are encryption neural detection. These features remain visible across all encrypted traffic. Efficiency. Fewer features reduce processing overhead, supporting high-speed detection. Privacy preservation. Avoiding payload inspection ensures compliance with user confidentiality. Resilience. Timing patterns are harder for attackers to manipulate without degrading performance. Coming down to our dataset, we have used the CIC-IDS 2017 dataset, which is quite large enough with around 80 plus network flow features. It has all possible attacks that we can foresee, such as web-based attacks, brute force, DDoS, and so on. And we have also filtered TCP and UDP, which are the two titans of network communication, for our analysis. And hence, we can say that this is a wealthy enough dataset for us to go ahead and perform our analysis. In terms of problem approach, our approach emphasizes extracting and analyzing time-based traffic patterns such as flow durations and packet intervals, developing lightweight models for scalable real-time intrusion detection, and benchmarking model performance on both regular and encrypted-only traffic using metrics such as accuracy, precision, recall, F1, and AUC. With respect to our proposed methodology, this is how we have tackled the problem. Data collection, we have aggregated TCP/UDP sessions to ensure diverse and comprehensive network flows, used existing ground truth labels such as benign and malicious for classification. In terms of feature engineering, we have focused only on temporal features like inter-arrival times and active idle durations. As part of pre-processing, we have removed duplicates and handled missing values to enhance data quality. With respect to model training and testing, we have deployed various classifiers, including tree-based and linear models, to learn from time-based metrics. And finally, we have evaluated our model to measure performance metrics such as accuracy, precision, recall, F1 score, and AUC. We will now move ahead with the data preparation stage, and it will be taken care by Ketki.
Thanks, Raji. So coming to the data preparation part, initially we had a large data set with over 2.5 million rows and 86 features, which had content and time-based features. To focus on encrypted and protocol analysis, we removed content-based features, keeping only 33 time-based features. We also cleaned the data by removing null and duplicate values and filtering out rows where the protocol was 0 or missing, as these are invalid or incomplete records. So after doing the processing, we got the regular traffic data set, which is almost 2.9 million rows, and the encrypted subset has almost 4 lakh rows. Both are retained only the selected time-based features. So at the network level, there are two main transport layer protocols, that is TCP, which is a protocol number 6, and UDP, which is protocol number 17. To isolate only the encrypted flows, we filtered out all UDP records by selecting only the traffic where protocol equals to 6, which corresponds to TCP. This ensures that our dataset did not contain any non-encrypted flows. This is the ABT table, which has description about the descriptive features and the target variable, which is our label, benign or malicious. Here the temporal matrix captures timing patterns like flow duration and inter-arrival time, which helps understand overall traffic flow behavior. The directional IIT matrix, this is same as temporal but computed separately for forward and backward directions, useful to detect imbalance or asymmetric traffic common in encrypted flows. Activity matrix tracks when data is being actively exchanged, active time versus the idle time, which is useful for spotting bursty or stealthy traffic. Throughput rates are measured flow speeds, that is flow byte per second or flow packet per second. These are the protocol metrics that identify the transfer protocols TCP and UDP. So next part will be data exploration taken care by Sheetal.
Thank you, Ketki. In our first step of data exploratory analysis, we examined the distribution of benign and malicious traffic. In the regular dataset, we observed approximately 1.74 million benign flows, whereas there were 5,56,000 malicious flows, which is roughly a 3:1 ratio. But when we filtered only encrypted traffic, there were around 3,76,000 benign versus only 75,000 malicious flows, nearly a 50:1 ratio. When analyzing regular traffic, we broke down malicious activity into 4 categories: top, mid-tier, stealthy offenders, and rare but impactful. DOS Hulk and port scan comes under the top attacks. Infiltration and heartbeat comes under the rare but impactful attacks. The top attacks accounted for nearly 70% of all the malicious flows. This diversity highlights the necessity of broad spectrum intrusion detection models that can handle both volumetric and subtle threats. Next, we isolated encrypted TCP traffic, revealing a very different threat profile. SSH Potator, a brute force attack tool, dominates the landscape, making up to 79% of the encrypted malicious flows. Portscan comprises the remaining 21%. Other attack types become nearly negligible once the encryption was applied. This narrow threat spectrum allows us to focus our model tuning, especially on SSH and scanning behavior. We also studied traffic characteristics like flow duration and session behavior. The dataset showed a right skewed distribution, meaning most connections were short lived. However, long-tailed outliers persisted, indicating unusually long or stealthy sessions. Understanding these patterns helps in designing models that can distinguish between normal short sessions and longer malicious interactions. This slide analyzes how different attack type behaves in terms of idle mean between the packets. For example, DOS Hulk attacks produce very high and consistent idle times, suggesting aggressive bursts followed by pauses. Whereas in contrast, infiltration attacks show more variable idle times, which makes sense given their stealthy nature. Interestingly, slow attacks like slow Rheosis and slow HTTP test are designed to operate slowly and avoid triggering alarms, which is visible in their idle time distributions. The next part will be taken care by Debika.
Thank you, Sheetal. So coming to the model building, so we split the dataset to 70-30 for training and testing. During the pre-processing, we handled missing values, normalized features, and encoded categorical. We focused only on time-based features which remain visible even in encrypted traffic, and trained 5 models from knife-based to random forest and XGBoost, and also evaluated them using accuracy, precision, recall, F1 score, and ROC curve. Moving to the first model, that is the knife base. So this model assumes feature independence and is known for its speed and its simplicity. On regular traffic, it performed modestly with an accuracy of 78% and F1 score of 0.42. But on encrypted traffic, the performance dropped drastically. Accuracy fell to just 54% and F1 score dropped to 0.078. So this shows that knife-based struggles to handle encrypted flow patterns, likely due to the absence of strong feature independence in our time-based attributes. Moving on to the next slide, that is the logistic regression. So logistic regression, linear model used for the binary classification. On regular traffic, we can see an accuracy of 82% with a precision and F1 score above 0.58. When applied to encrypted traffic, accuracy jumped to nearly 99% and precision stayed high at 0.96. However, the recall dropped to 0.39, meaning many malicious flows were missed. So this indicates that while it confidently identifies benign flows, it's less sensitive to attacks in encrypted settings. The next model is the support vector machine, similar to logistic regression with 82% accuracy on regular traffic.
It has achieved 98.7% accuracy on encrypted data, but with low F1 score 0.39. So SVM works well for simple patterns, but struggles with encrypted data without kernel tuning. So even though it's possible to analyze encrypted network traffic using just time-based features, the simpler machine learning models such as naive-Bayes logistic regression or basic SVM struggle to perform well. So these models often show lower precision recall and F1 score. So more complex models such as random forest and XGBoost are better at handling these challenges, which will be taken by Aishani in the coming slides.
Thank you, Devika. Now let's look at random forest, one of our top performing models. So it has shown nearly perfect accuracy of 99.77% for regular traffic, and it went up to 99.95% for the encrypted traffic. The F1 score for encrypted data also improved after tuning. Moving on to the next slide, we have performed hyperparameter tuning in order to achieve better metrics. So in our hyperparameter experiments, we tested several combinations, and we observed that increasing the tree count generally improved performance, but beyond a certain point returns were minimum. And we also experimented with min sample split, and higher values helped with generalization. Overall, careful tuning gave us a very strong and balanced model. Next, we look at our XGBoost model, and this model is our top performing model. It has achieved an accuracy of 99.97% on encrypted traffic and an F1 score of 99.13%, which is incredibly high. Even in the highly imbalanced encrypted dataset, XGBoost maintained excellent precision and recall. So if we compare all the models and summarize the performances, random forest was reliable, interpretable and extremely accurate, especially on the encrypted data. XGBoost is the unbreakable shield that it emerged as the strongest, delivering near perfect results on all metrics. Naive-Bayes mainly struggled, especially with encrypted data. Accuracy and F1 dropped significantly. Logistic regression demonstrated the accuracy paradox. The accuracy spiked from 81 to 98% on encrypted data, but the F1 dropped slightly and recall halves. So it means that it masks the true attack detection. SVM was precise but missed many attacks, making it unreliable in a real-world intrusion setting. So ensemble models like random forest and XGBoost dominate in this context. Moving on, we look at the ROC curves for the random forest. The AUC is almost nearing 1, which means the model almost perfectly distinguishes between benign and malicious flows. This holds true even when evaluated solely on the encrypted traffic. Moving on to the ROC curve for the XGBoost. XGBoost goes a step further with a UC of 1, which is the perfect score. The curve immediately reaches the top left corner, showing it captures all attacks before any benign flow is misclassified. The performance remains consistent even if in the challenging encrypted only subset. So it's a clear winner in terms of classification power. Moving on to our final insights. So our final recommendation would be XGBoost should be our primary model. It generalizes well, handles encryption reliably, and has the highest F1 and recall scores. Random forest is our fallback option or backup, especially useful when we need model interpretability or a faster inference for real-time use. Both models show that encrypted traffic threats can be effectively detected using only time-based features. Now I'll hand over to Raji for concluding.
Thank you, Aishani. As we wrap up, let's take a look at the future scope and how this can work on a real-world environment. Real-time feature extraction and scoring. We aim to implement the system at the network edge, where time-based metrics like flow durations, inter-arrival times can be computed in real time. These metrics can then be immediately passed to the trained model for live threat classification. Low latency model serving. The trained XGBoost or random forest model can be wrapped in a lightweight inference service capable of responding to network events within milliseconds, critical for preventing attacks in real time. Automated monitoring and retraining. As attackers evolve their strategies, the model must too. We propose setting up a pipeline to monitor model performance over time, automatically flag concept drift, and retrain periodically using updated data sets. Feature and protocol expansion. Beyond time-based metrics, future iterations could also explore encrypted agnostic features such as packet sizes or handshake timings. Also, we plan to extend protocol support beyond TCP to include encrypted UDP transports like QUIC, security operations integration. Finally, we envision integrating this model into existing Security Operations Center dashboards, providing analysts with real-time alerts, confidence scores, and visual explanations for faster and more informed responses. In short, our model is not only accurate but also deployment ready with clear paths to integration, automation, and scalability. Thank you.